Hey, how's it going, everyone? We're going to do Pytorch Autograd Part 2. We did Part 1 yesterday. And based on where my scroll bar is, I don't know if you can see this right here. It's kind of a little scroll bar. We're like a fourth of the way through. Maybe we can get through this a little bit more quickly. I'm not sure. But this is a lot to go through just for Autograd, which is the whole Pytorch framework itself. It's the entire framework itself. So, let's see here. Oh. So let me figure out where we left off. All right, finally, let's compute the single element output when you call the backward on a tensor with no arguments. A tensor with no arguments. Backward on the tensor with no arguments. What does that mean? Are we going to do that? Is that actually going to happen? They just say that in a comment, and they're like, nope. Okay, wait, one second. All right. So they want us to do a dot sum. How's it going there, Seek the Vault? Welcome on in. Happy Wednesday. We're continuing our Autograd. We're going to make it so that way we know as much PyTorch as we possibly can, and we can call ourselves PyTorch experts. That's what we're going to do. And that's the plan for today. So this is the part, call backward on a tensor with no arguments. And then they just, all right, so we're going to try it. We're going to call backward on a tensor with no arguments, and we're going to see what happens. I don't think I've ever done that before. I always do it on a loss, which is, it counts as a tensor. That counts as a tensor. Hey, Sergio, it's good to see you. Serge. Good to see you. Welcome on in. Happy Wednesday. We're going to become PyTorch experts, you guys. We're going to try this. Even though they don't have it in any of the code anywhere, we're just going to try it anyway. First though, let's do print d.sum. I'm kind of curious how this is going. Yes, nice. Perfect. Let's make it happen. Let me uncomment some of these things here. I want to remove those things. So that way we can see a little bit more about what we're doing here. Okay, so it's also tensor. So this, hey Kyle, good to see you. Hey, we're going to chat later today. Looking forward to it. All right, so we've got our d.sum, which is also a tensor. And then also probably if we do a loss, right? Sum.backward. Okay, so this is wait, hold on a second. Wait. How do you derive a sum? There's no derivative. You can't do it. Polishing pitch deck. Hey, nice. All right. Looking forward to it. Absolutely. All right. So this is interesting. How do we backward a sum? I suppose you could just average it out and make a whole a gradient. You can't reverse it. It's unreversible. All right, so what if we do backward on D? Print D dot back. Let's do it. Print D dot back. Can you even do this? I don't know. It's a tensor, so you should be able to, right? When you calculate the loss, it also counts as a tensor. So backward. Let's see here. Didn't even let us do it. Did I type it wrong? Did I type backward wrong? Sometimes I do, you know. Backward. Did I type that wrong? Looks fine to me. It says you can do it right here. Finally, let's compute a single element output. When you call backward on a tensor with no arguments, it expects the calling tensor to contain only a single element, as is the case when computing a loss function, which is right. That's what we're talking about. Computing a loss function. But it says on a tensor, what's the error say? Grad can only be implicitly created only for scalar outputs. Oh, wait, isn't? Okay, so we should be able to do dot backward like this, right? What if we do dot backward here? Sounds esoteric. Well, it kind of is. It is a little bit exoteric. It really is. You're not wrong, Kyle. You're not wrong. So there we go. Okay. And there's no data returned on the backward. It just computes the gradients. Only when you have a scalar. Okay, now we know. It's got to be a scalar. It can't be anything else. If it's something that's more than a scalar, it won't work. All right. A scalar just means a single value. That's what that means, right? So, all right, I just bring this over here. And we can see that the scalar is 25 in this case. See right here on the screen, 25? That's what that is. That's all it means. A scalar is a single value. Easy. All right. I feel like I want more than that, though. I need more than that. I feel like I'm being limited. Each of the grad functions stored within our tensor allows you to walk the computations all the way back to the inputs with the next functions. Oh, so they've got built-in next function properties. Do we ever need to use that though? I don't think we do. We can see below that drilling down on this property, D, which I believe is just our variable that we have right here, right? D right here. The gradient functions. Hey, thank you for the hearts. Appreciate it. Good to have you here, Kyle. For all the prior tensors, note that a.gradient function is reported as none. Yes, we just saw that, indicating that was an input to the function with no history of its own. Okay. All right, that sounds fine. Oh, so we got a grad function here. Let's see what that looks like. All right, so we got a grad function. Let's hide these guys. We go print d.grad fn. What is that? What is that right there? What is that? I'm actually kind of curious. Where do you find out what that is? Add back. Oh, neat. Okay. But why is it only one when we have obviously multiple here? Shouldn't it be like an array or something? Because the add backward, I see we've done an add here, but we've done multiple operations, right? What if we get rid of 1 plus 1? Is it gonna be molt? Is it gonna be molt? Yeah, molt backward right there. Molt backward. Okay. What about next functions? Oh, okay. Here we go. Check this out. All right, now we're getting into it. Now I'm like, shouldn't there be more than one? There is more than one. All right, now we're on the right track. All right, this is great. All right, so dot next functions with an S. Okay, let's see what we get here. None. Oh, wait, no. Okay, no. Okay, this is exactly what we want. Okay, we've got multiple here, right? Wait. Yes. Hold on a second. Wait. I see both. I see add and mult, which is what we've done right here. We did add and mult right here. So this is the first one, and this is the next one. So add, we'll unwind it, right? Because you gotta go in the reverse order. PEMDAS, right? I believe, right? PEMDAS. Multiplication, division, parentheses, exponents, right? What is that? The order of operations, parentheses, PEMDAS, exponents, multiplication, division. I thought division was before multiplication. I forgot about that. Addition, subtraction. Okay. So that's the order. And then you go in the reverse, right? So add first when you're doing backward. That's how that works. Okay. We're learning new things now. All right. I love this. Oh, wait. Whoa. What? That's a little odd. All right. Do you really have to do this? This is weird. 0. Oh, it is. I don't know why they did it like that. I don't know why there's structures like that. It's very odd. It's very odd. It's very odd. Let's try it though. Let's try it to see if we get anything interesting out of it. So 0. Because that's going to unwrap this right here. This object right here is going to have the next. So it's going to unwind even further. So the next one should be another multiplication, right? Another multiplication. And then we should see the partial derivative of sine. And then we could get up to here. Okay, so let's do next functions. 0. I think we'll just do 0 like this. Be easy. And then we could do next function again. Like that. And it will also be molt, right? It's also molt. Whoops. Also multiplication. Yep. Multiplication. We got both of them right there. All right. Oh, whoa. You remember that? Oh, wow. The card game? How do you remember that? That was like from streams ago. That was from multiple streams ago. That's crazy. Good memory. All right. Then we should be able to do this again. Let's do this one more time. And 0. And then we will do another dot next function. And this one should be the inverse of sine. Right? Right here. That's what that should be. So let's see if we did it. Let's see if we figured it out. It is sine backwards. All right. Now we know where Autograd comes in. Although it's in a weird structure. I'm confused about it. Maybe they did this on purpose for future design patterns or for some other consideration. I'm not exactly sure. Though we just uncovered the future of Autograd. We just figured it out. Let's see how far back it goes. Let's see how far back we can make it go. All right. Let's see if we can make it go all the way back to the beginning. We'll do like this right here. Let's copy and paste this. Actually, wait. We'll bring it down. We'll bring it down a couple more times until it can't go any further. Copy that. Paste that. Paste that. Paste that. Okay. Now we backed it up a few more times beyond where it needs to go, because we got it up to sign, and then whatever our initial there's nothing here, unless it's gonna capture this, which I don't think it would, because this is just part of the generation. Okay. So we should get an error maybe. Okay, we do, because it doesn't exist. 32. All right, that's exactly what I thought was gonna happen. Tuple out of range. There it is. Accumulated grad, the very beginning. Oh, that's very satisfying. Right here, you guys. The origin of your accumulated gradient. There's nothing left. You can't go any further. We maxed it out. All right. Thank you for the hearts. Thank you for the reactions. None. Oh wait, it just crashed for me. Oh wait, no. Why does it say none? For I get accumulated gradient. I get something different. Weird. Oh well. And we're looking good now with all the machinery in place. How do we get derivatives out? You call the backward method on the output and check the inputs grad property and inspect the gradients. You can only do that though. You can, let's look at the grad. Oh, the inverse of sine. Look at that. Wait. Oh, that's really cool. Okay, so we print both. We'll print both of them. So I believe that's the inverse of sine. Okay, so that's the backward. That's the gradient, because we calculated the gradient, which is the inverse of sine. Right? Because that's A dot detach. Okay. Let's try print A and A dot detach. A dot gradient. Okay. So we should be able to say out equals A dot backward. Can we wait? No, grad. A dot grad, which we already ran the backward on. Do we have it here? We have to run the backward here. Okay. So we need that. If we don't do it. Hey, Mark Lemon, thanks for saying hi. Thank you for clicking the hi button there. Good to have you here. Welcome on in. We're becoming Pytorch experts, as you know. We are learning all about Autograd, and we're figuring it out. We've seen behind the scenes, and we know how the graph is constructed now. Before it was a mystery. We've figured it out now, just by walking through the tutorial. Who would have thought walking through the tutorial would be useful? I don't usually do that. I usually just jump straight into the code and then start reading some of the, docs if I need it. If I need help, I read the docs. But walking through tutorials is actually kind of fun. Okay. It is work though, don't get me wrong. So we are doing a backward here. We don't need to print that. We're just gonna say out equals D. There we go. And then we don't need to print any of these anymore because we already know what the deal is. I want the, let's do the backward. So we got the backward, and now all we have to do is A dot gradient, which will be the inverse of sine. Wouldn't that be B though? Wouldn't that be B? I think that would be, wait, A dot grad detach, A dot, okay. Let's find out. We'll do a couple of them. Let's see, where is our mat? Okay, so we'll start with this. I'm kind of curious. We'll look at that, what we had before, and then we'll look at the gradient real quick. Let's see here. Younger people are also lucky to have Steven doing the live work. Yeah. My mentors practiced mostly marketing fluff and kept industry secrets. Oh, the secrets. I'll tell you all the secrets. I'll tell you everything. I'll tell you all the things. Stephen OB is awesome. Hey, thank you. I appreciate it. Great for you to say that. You guys are so nice to me. You're so nice. Thank you. I will tell you all the secrets because you're flattering me. Okay, I'll tell you all the secrets. Hey, Stephen, how's it going there, HS? Good to see you. Happy Wednesday. Pytorch experts are the things that we're going to become. We figured it out. We just in the first 10 minutes of stream just now, we saw into the graph, the entire Autograd. We figured out Autograd SVR. Good to see you. Welcome on SVR DAC. Good to have you here. Hello, happy Wednesday. You glaze a lot. It's genuine. Oh, nice. Well, appreciate it. I appreciate it. Thank you. I appreciate it. All right, Grad. Also, we want to. Okay, here we go. Wait. Oh, no. A detached B. Do we have B? We got B. All right, so I should be able to run this. We got an error. All right, where's that line? Oh, out. A.grad. Of course. Grad, where's that at? Here. The out is not going to be. We want backward. No, we can't. That won't work. That won't work. Do we do that? I was about to do something there. So grad is a yes. There we go. All right, perfect. All right, here's the sine wave. Is that an iterative method? Iterative, it's all iterative. It's a whole big giant for loop. It sure is. This is that's usually what computers do. They go over a list of elements for the most part. Or it's just being silent and it's just being stationary. And there's not much to it. You know it. All right. So this is our sine wave. Now we're going to see something different. We're going to see the inverse of the sine wave. Did we do backward? All right, so we did backward right here. And then I want to do a different one. Let's do a detach, a dot grad dot detach. And we don't need that. Like this. Now we should see our original sine wave. And then you're going to see something different, the inverse. You're going to see the gradient part of it. All right, so let's look at the inverse. Yeah, right there, we got it. Right, it goes. Wait, is it the exact opposite though? I don't think that's the exact opposite. It would be like, it'd be flipped. However, this is the gradient. I say, yeah, party poppers. Hey, look at that. We're checking these out. This is pretty neat. What if we did b.grad.detach? Let's see what that looks like. I'm kind of curious about that. Let's do b.gradient. I want to see what that looks like. Oh, it is the sine wave. It is. It's straight up. Okay, so it won't be calculated until we get to A. Understood. All right, what does C look like then? See what C, or is that not even work? It might not even work. All right, let's see here. Oh, it won't. Okay, got it. Okay. So that will give us the grad. The sine waves are waving. They sure are. They are waving. We got some waving sine waves here. What if we did cosine? Can we say cosine like that? Or is it going to ask us to do... Can we do cosine? I think we can. Yep, okay. Oh, it is cosine. That's the... no way, really? Wait. Sine, cosine, I guess they're the opposite, right? Yeah, they sure are. Look at that. That's how you derive between the two, sine and cosine. Hey, Jinlu. This... Oh, Jinlu. Welcome on in. Good to see you. All right. What does backward do? It calculates the gradients between all the different layers. So you see how we've got a layer here. We got another layer here. And the C, so you got D, you've got D, and you got C, B, and A. These are our layers, right? Layer 1, 2, 3, and 4. We got 4 layers. 4 layers. What are you doing? We are becoming Pytorch experts. We're going through every single Pytorch tutorial, and we're going to learn everything we can about Pytorch, so that way we have a full understanding of what it is. And then we're going to start building things. We're going to build our own transformer. We're going to build our own GPT. We're going to build a whole bunch of different models. We're going to build vision transformers. We'll build generative AI. We can do it using Pytorch. We'll do it using Pytorch. I've built transformers before in other languages from my own from scratch. We've built our own AI frameworks from scratch, live on stream. Now we're learning Pytorch to see what we can. Maybe we can learn something from it. Maybe we can get something grand. I'm looking forward to it. Becoming a Pytorch expert seems like a good plan to me. We're going through Autograd today. Yeah, we are. We're becoming Pytorch professionals. We sure are. Okay. La la la. Yep, we just did that. Layer 1, 2, 3, and 4. We calculate the output, which is a scalar, and then we run backward on the scalar. Backward, right? So out. This is what we do. So you say out dot backward. this is going to create the gradient. It's going to go backward. It's going to unwind each of these operations. So instead of adding one, it's going to subtract one. Instead of multiplying by 2, it's going to divide by 2. Instead of using sine on wave, it's going to do cosine, because that's the inverse, right? It's derivative. There you go. That's the answer. Hey, thank you for subscribing. Can't say what your name is there. I don't know how to read that language. Good to have you here. Thank you. Welcome on in. Happy Wednesday. We are becoming Pytorch experts on this channel. We're going to walk through everything that we possibly can. Oh, hey, look. It's the leaves. Right. So is this? Yeah, it is. It's right there. Look at that. Oh, that's so neat. We figured that out. We're like jumping ahead into the tutorial. I'm like, this is what it's got to be, right? This is what it's got to be. And it's just describing right here the derivative, which should be 2 times cosine A. We figured it out. Look at that. We know what we're doing here, you guys. Looking at the graph above, that's just what we see. It sure is. It sure is. Private Akdela from Russia with love. All right. I don't know exactly what that means, but I think it sounds good to me. Beware, beware you guys, that only leaf nodes of the computation have their gradients computed. Only the leaf nodes. If you tried, for example, print c.grad, you'd get back none. Because c is not part of the picture. It's right here though. It's in the graph. It's connected right there. Right here, it's connected. Why not? It's Russian. Okay. Understood. Hey, Dar, good to see it. Can you build image video generators? Yes, we sure can, like Nano Banana or VL. We know how to do it. We sure do. We're going to be learning everything we can about Pytorch, and then we're going to start getting into those kinds of things. SQ Lighter, hey, how's it going? Hope you're doing okay over there. Say hello to Neva, your sister. Do you use Ada Delta a lot? What is Ada Delta? I don't know what that is. What is Ada Delta? What is that? Ada Delta. Adaptive learning rate method. Oh, I've never used it before. Hey, Never, you're here too. Hey, cool. Welcome on in. Good to have you guys here. I've never used Ada Delta, adaptive learning rate method. Or have I, and I didn't realize it, because I've done that before too. Add a parameter group to the optimizer's param groups. This can be useful when fine-tuning a pre-trained network. Interesting. Oh, we might get into it. Who's Neva's sister? Lighter. Exactly. What if I made crypto market prediction model? Ooh, now you're getting into it. You sure can, especially. Here's why the crypto market is just so much better when it comes to AI. Because I'll tell you why. You've got so much more data, and it's fully public. Right? So is the stock market. However, there's just not as many trades that are public. You don't really you see volumes and like aggregates. You might not get an order book. However, you can get the full order book on any of the crypto exchanges, and usually without a cost. It's for free. Ada Delta is a pure precursor. To Atom. It's a precursor to Atom. So it was before Atom. Or Atom made it better though. Ada Delta aims to dynamically adjust learning rates so that they don't shrink to the point where learning essentially stops. Stands on the shoulders of algorithms before it, making an advanced optimization. Stochastic gradient descent method based on adaptive learning rate per dimensions to address drawbacks. Ooh, all the drawbacks, you guys. It's a subset of Atom. Got it. Okay. The more we know. Thank you, Neva. Might be mixing it up with Autograd. Got it. No worries. And then, so Autograd. Okay. This is, all right. Autograd versus Autograd. 2 different things. I mixed that up as well. You love this song? I know, it's a good one. I like this song too. Hey, Clinker Plays, thank you for the 100. Meh, XG Boost is king. XG Boost is the king. Is it? We got to learn about XG Boost. All right, XG Boost. I've heard about this many times. I don't know if I've ever extreme gradient boosting. Oh, to the max. All right, is an open source, highly efficient and scalable machine learning library that implements optimized gradient boost decision trees. The GBDTs. It excels at classification, regression, and ranking problems, providing superior performance through parallel computing, regularization automatically to prevent overfitting, built-in handling of missing values as well. Whoa! It is all-in-one Super Army Swiss Army knife. Wow, check that out. That's great. Hey, thank you, XG Boost. Clank Players. Thank you, Clank Player. Plays. Thank you, Clank Plays. Thank you, exclamation point Party Popper. All right, let's type that in. Thank you, thank you, thank you. Appreciate it. My gratitude to you. Oh, it's my pleasure, man. Thank you. Oh, it's amazing. Optimized distributed gradient boosting library designed for flexible and portable. Implement machine learning algorithms. We're gonna have to. XG Boost in PyTorch. Do we get that? Do we get that? XG Boost and PyTorch are distinct machine learning libraries. Oh wait, they're different. XG Boost excels at tabular data problems using gradient boosting, while PyTorch, well, a completely separate thing. Flexible deep learning framework, neural networks. Can we use the XG Boost patterns in PyTorch? That's what I want to know. That's what I want to know. One common approach using the outer learned features of PyTorch deep learning model input for XG Boost model, or the other way around if you want. All right. Sounds like a good idea. I'm curious about it. I'm very curious. PyTorch automatic differentiation autograd engine can be used to calculate the gradients and the Heissens for complex custom loss functions, which are then passed to XG Boost during training. So are these two different things? I want to use XG Boost design in PyTorch is what I want to do. Tabular structured data classification, regression ranking, unstructured data, deep learning. Oh, okay. I get it now. All right. So XG Boost versus Scikit then. XG Boost versus Scikit-learn. This is a better comparison between these two guys. Do you ever use ensemble learning for classification problems? I've not used ensemble. I've done a lot of classifications before, or I might have done ensemble learning and not realized it because I don't know always what I'm doing. I'm just clicking the buttons and it works. What's the most iconic thing about yourself or your channel for some little project I'm doing? Most iconic thing? Well, let me see. One of our, we had a magician use our technology on, I believe, America's Got Talent. On stage, live. You want to see? That is probably the most iconic thing. Well, that's one of them. It's one. Don't worry. There's more than one. That one was really neat. That one was like kind of like really fun. All right, let me see if I can find that. 1 second. I'll show you. Let me pull it up here 1 second. Videos, visibility, private. My private video sections, you guys. All right, 1 second. All right, here we go. Private videos. Okay. It's blocked because it's got copyright stuff on it. Yes, that's wild. Would you say the proprietary PubNub dance is pretty iconic? Yeah, that's a pretty good one. Yeah. That was fun. That one's public, though. That's a public video. All right. I'll have to find it 1 second. All right, so magician on America's Got Talent. Can I go into it? Oh, that's me. Long time ago. All right, 1 second. Let me see if I can find it. I want to go. Yeah, I want to actually go to the video. Okay, here we go. Let me see if I can find it. There's a few shining moments in history that are always fun to talk about. My hair. Jump back and. All right, 1 second. And the moments that you made it to the mainstream, and for example, the The Late Show. Check this out with Stephen
Whoops, sorry.
Colbert and Periscope. Check this out here.
How many 20-somethings in Silicon Valley are not millionaires at this point? Like 4?
Literally of having a TV show. What if we could give everyone the possibility of having a TV show?
Well, then no one would watch my TV show. Why? What's the purpose of having professionals if every person can have their TV show and go, hey, welcome to the show?
As with the internet generally, there are a number of memes that have unfolded, and one that I have a hard time explaining is literally folks would just go live and viewers...
Hey, Claude, good to see you.
And the broadcaster would be like, oh, that's kind of weird, but sure, here's my fridge. And people would be like, holy you know, that's your fridge.
Okay. Do you watch CBS Late Show? Question mark?
Hey. Wait, do you watch CBS Late Show? No, I don't. I'm too busy sleeping.
What'd she say?
I don't know. I didn't hear what she said.
Wow, what?
She said no?
But yeah.
You might want to
Yeah,
tonight.
Yeah, that's using my technology. Isn't that crazy?
So we got a support email that came into our support channel, and they had an urgent support request. They wanted us to help them out. They're going live with a big something, and they needed help for some bug on the iOS app, something that they needed help with. So we checked it out. We looked into it, and we're oh hey, look, they're only a few blocks away. Why don't we just pop on over to the office at the end of the day? We can solve their issue. No big deal. And we went over. It's just me and a Garish, which one of the SAs at the time. We popped over. It looked like regular mobile dev shop with a bunch of phones, kind of like all over the place. There's something different though, something a little bit of weird. Like there were what appeared to be I recognize, are those celebrities on the phone? They're like, yeah, it's like, I recognize that. Is that Aaron Paul? Like, yeah, it's Aaron Paul. Is that like, right? Are they live right now? Or are they like, yeah, they're live. Well, oh my, whoa, okay. Which is kind of like a little star story. So we were like, all right, well, we're here to help solve the issue. What are you kind of running into there? So it was a history API issue. We knew what the deal was. We helped them with their challenge, and on the way, made it simple. Jumped over, went to visit, and boom, solved their issue. I kind of like that. I love interacting with customers in that fashion and getting to talk to them and solve their issues. That's like why we're here. All
right, get on with it, Steven. Get on to the next thing.
Next story. We kind of have we notice like there's a story of magic. There's something like majestic.
Here's the magic part.
PubNub, where we see our customers shoot for the stars, and they make it all the way to Hollywood. Check out this next customer and kind of what they did and what their story was. So they invited us down to Los Angeles to the America's Got Talent studio. They wanted to make sure that when they were presenting on stage using this technology, it was like kind of a cool magic show approach, that everything was going to be okay. Of course, there's PubNub, so everything just worked. We got Jazz Deep and I think it was Jason at the time. We got to go down and go backstage, meet some of those folks, Simon Cowell and the crew. They were sort of there. It's like the sports kind of neat. And our act on stage was sort of reveals the magic. Like on a TED Talk, check out what our Tom London, what he
This is on America's Got Talent.
How did he do it?
That was the best moment of my life. And did it with their phones. It was really, really cool. So how did I do that? Well, let me break it down. I've never told the story. I'm very excited to share it with you. I called it life hack. So what my goal was to do was to be able to get everyone's phones to be controlled by me, the whole phone. So the design challenge of that is like, okay, well, how can I control the phone? So what I did is I actually had my assistant come on stage wearing a jacket, looking like a techie, and he was like, everyone needs to go on this web page, we're doing a thing, and everyone's like, okay, I'll follow along, and they all did it. So now everyone's primed and ready, they've got no idea what's going on. So how did I make this little application? It's actually quite complicated. What's happening is that QR code forwards you onto my server, which is running lifehack.tech, another expensive domain name. When you land on the web page, I use something called PubNub. PubNub is a real-time data messaging platform. What it does, it basically is like WhatsApp for the internet. So if you've got like an app or something and you want to communicate between people and servers, you can use PubNub to do that really, really quickly. So what it does is it sends like a little text message, and it's so small, it takes milliseconds to get from A to B. And this scales up to, well, theoretically millions of people, all unified together in this one big WhatsApp group over the internet. So yeah, that was my moonshot right there. It was really funny how I got in touch with the guy. So actually, the guy who kind of started this company.
I forgot about this.
Huge company.
I forgot about this.
Blum, the CTO. I found him on LinkedIn. I dropped him a little email. I was like, hey, I'm a magician. I do some magic stuff. Yo, can you help me out? And he came back to me and he was like, PubNub is magic. Okay. So I'm sitting there like all excited, like,
I forgot.
San Francisco Big Shot just sent me an email. 2 seconds later, are you a real person? What?
All right, so next.
Okay.
When you go in America.
All right, that was it. Oh wow, man, yeah.
When you
It
pass,
keep-
right?
There's more to it. Well, there's more to it. Yeah. I don't know. We could keep going. I don't know. Where are we at here? I do want to get into PubNub is magic. I know. We could do more. Maybe we'll show more later. We'll show more later. Is what we'll do. We'll show more later. Let's get back into our Pytorch though. That was a lot of fun. I forgot about that. That was pretty fun. So that was just for you guys. Just for you guys. Only you who are seeing just now, you got to see a moment that is a unlisted, well, a private YouTube video from many years ago. How long ago was that? That was 5 years ago. That was 5 years ago, you guys. Right here. You can see 5 years. Boom. Iconic. That was fun. Nice. Yeah. That was fun. I forgot what that was like. I was like, oh yeah, I forgot about that email. That was really great though. That was a lot of fun. All right. Let me see if I can unwind now of that and get back into something that's Pytorch. Some AI stuff now. There will be time where I will be asked to design PubNub in a systems design interview. It would be magical. I know that would be awesome. I feel like there's still some magic there. I still feel like it because every time I use it and then something you get to see live reality, like real things communicating, and then you as a human get to see the outcome. I feel like there's still magic there. I feel like still magical. All right, that was just for you guys. Only you get to see it. That was a little sneak peek at a private video from 5 years ago. You can't access it anywhere, and I can't make it public. It's actually unpublicable because because visibility is blocked. Yeah, I can't do anything about it. It's stuck. It's stuck because copyright protected content, which hopefully. That doesn't like bleed over into this video. If it does, I don't have to like edit it out. Others, Harry Potter is magic. However, Stephen Blum, the PubNubber, the Python magician. Hey, I hope you like this. Yeah, I know exactly. Appreciate the sneak peek, man. Hey, you're welcome. Hey, you're absolutely welcome. So SQ Lighter, if you're still here, let me see. I know I didn't answer your question with that video. I know we didn't answer that question in your video. Is there anything more about yourself? Like, what do you usually use, or something known which is kind of a meme? I don't know. Maybe that dance video? I mean, if you're talking about tech or something else. So like pubnub.com / and you put a bunch of random letters in, you'll get me dancing. Oh wait. Yeah, okay, there it goes. Yeah, you'll get me dancing right there. Which was even longer ago. That was even longer ago. I think that was like, what was it? 7 years at least, 7 or 8 years ago. So yeah. The secret magic sauce isn't Python, it's Steven. Hey, yeah, there you go. Bro, meet you tomorrow. All right, sounds good, Claude. Ben's best streaming day, Steven. PubNub, choose one. Exactly. The chosen one. All right, let's get back into it. I have all right, so SQ Lighter, I have a patent on measuring internet latency. I don't know about that one. I don't know if that's very interesting. Let's see here, linked here. I've got it on here. I've got it here somewhere. Let me go to me. Where am I at? Steven. All right, this might be interesting. Here's my patent, you guys. On Transmission communication network selective. Nope. Method for detecting a wide area. Here we go. So this is a pattern that I like. Let's see. Bring it back. Back, forward. Here we go. All right. So SQLiter. If you're still here at SQLiter. That one might be interesting. All right. Let's get back to Autograd, you guys. In your blockchain background, use the IPFS PubSub. Looks like we gotta migrate to PubNub now. Oh, that would be, you could do that too. In fact, that's what we were doing. We were building PubNub into our own blockchain. Because you just need a transmission network. You don't need it, it doesn't need to be fancy. That doesn't need to be fancy. Were you supposed to destroy the real-time messaging infrastructure, not join them? I know, right? Anaka, Steven, if you were the chosen one. You were the chosen one. I know, I see what you're saying there, Kyle, I see. Hopefully you'll use that data in your project. All right, that sounds good to me. SQLiter, let me know. Also here anytime you got questions. Star Wars reference, yep. And exactly, becoming, yeah, and you said Anakin? Anakin Steven, right? Instead of Darth Vader or Skywalker. I remember that, I remember that. All right, let's get back into it. So we saw the leaf nodes problem. All right, Autograd and training. So now we're on to like the next segment here. We're on to the next segment, Autograd training. Okay, let's take a look at this. Let's see what we got here. Let me check real quick my phone. So that way I'm making sure we're on the right pages on things here. Looking good. It's loading, okay. Okay, we're good on time. All right, Autograd in training, you guys. Let's get back into it. We've got a brief look at how Autograd works. We sure did, and we understand it now. Hello, how's it going there? Alan Sockid? I'll say Alan. Welcome on in, good to have you here. We're learning how to become Pytorch experts, reading the tutorials. Today we're doing Autograd, and we're gonna learn how Autograd works in the training process. So probably optimization, which we saw the most important part, which is the back propagation, I think is the most difficult part of the picture. The training part is easy. Backward propagation is a little bit more challenging and probably the more complex part of this. By the way, geode error. We talked about a few streams ago. Still haven't been solved. What's the geode error? Oh, wait, I actually forgot. I actually completely forgot. Not even a little bit of forgot. 100% forgot. Geode error. How to easily fix geode not working for Geometry Dash. Oh, you mentioned something about a game and some sort of kernel and some sort of build and CMake. You're making your own CMake or something like that. Something like that. I forgot. All right. So let's get back into it. We're going back over to our training now. First, define a few constants of our model. The hyperparameters. We've got a batch size, dimensions input dimensions, hidden size, dimensions out. That's a lot of input dimensions. Tiny model? No, not with that many input dimensions. I mean the hidden dimensions, sure, because you're downsizing. So it's a 10 out classification problem. Geode is a tool that generates CMake. Oh, got it. Okay, thank you. Hey, Manihara, welcome on in. Manihara, good to have you here. Hello, Steven. Hey, happy Wednesday. All right, let's build ourselves a tiny model here, you guys, real quick. And then we're going to go through the Autograd section of this. All right. We're going to do Autograd and training. All right, let's close this. All right. Vim, we'll call this Autograd training.py. Python Autograd. Wait, is this a file yet? Autograd training? All right, perfect. Import torch. We're gonna have our batch size equals 16. Okay. We're gonna try to fully re-implement this exactly as it is. Something in GeoCLI you're building a mod, and Neva wouldn't help. Crazy, she lazy. Oh really? Wait, no way. I thought Neva would help. That's crazy. You just saw some someone made an MCP server for PubNub. Oh, yeah, someone did? Who? Clanker Plays? Who did that? Who did that? I'm actually getting curious about that. Tell me. You helped for hours? Okay, I was wondering about that. I was like, I thought it never helped. All right, so input dims equals 1000. Hidden dims equals 100. Hidden size, I guess we could say. It's not really the dims. And it's input size. I'm gonna say size. I like size better. And then output size equals 10. So now we got 1010. Perfect. What about like epochs and other things like that? I suppose we don't care. All right. Class tiny model. It's going to be torch dot. Is it model? Torch dot nn dot model. Like that. Okay. Def init self. And then we do super. There's some sort of super thing here. Okay. Super tiny model. Comma self. And then we just read this. I do not like having this part. I don't like this. When you have to implement the internals of any other framework using Python internals like this, using a dunder method in a side of a dunder method, it just feels dirty to me. I feel like since we have to do a super, I would rather, since we're inheriting, there's inheritance here, we could just say self.super like that, and it would take care of it. Like there should be a nice little easy method or something, or not require this at all, and then have the model be taking care of itself in a different way. Instead of using init, for example, we do new or something, right? Something like that, at least. And rather than having to do this, I think that. Not enough hours. Oh, some has to go ask the gender forms and stuff like that. It can't be bothered. Oh, all right. He can do it himself. I doubt it. Wait, you can try. You can try. Personal opinion: object-oriented program feels weird in Python. It sure does. Clanker Plays. It sure does. You'd rather go with Golang since they have a minimalist approach and it's cool. Golang. Yeah, Golang has a really good one. I like Golang. I like the coroutines, the channels. I like channel passing in Go. It's my favorite. Can you lower the background music sound a smidge? All right, there you go. Boom, background sound reduced. There you go. Background sound is down. Okay. All right, let's go into the rest. All right, so we're gonna do layer 1. Dim input dimensions, hidden, and out with a relu. Okay, so let's do this. All right, so self.l1 equals torch dot was it linear? Yeah, it was linear. nn.linear, and we do our input size, comma our hidden, and then we do self dot act. Well, we'll just call it rel torch, nn. By the way, there is a page, PubNub official docs for their NPC. Yes, there sure is. Is that what you were talking about? I was wondering if you were talking about that. How do we just rel you? Just like that. Self dot. Let's see. Yeah, we'll keep it rel. Then we do L2. Torch dot nn linear. This is the hidden, comma the out. Just like that. Okay. Looks good to me. Now, what do we do? All right, we're gonna do a forward. This is fine. This is fine. Def. I'd rather do like a sequential. Torch in and out sequential. So I'll say self. We'll change this up. Do we have to worry? No, we don't have to worry about it. Okay, self dot. I'll say seq equals torch.nn.sequential. And then instead of all of these layers like this, we're going to do it slightly differently. Like this. All right. No, that's too far. A smidge too far. And do we have to put it inside an array? I think we have to put it inside an array like that. Okay. And then we do commas for delimiting. You got blush on. No, that's just me. That's just ordinary face. I never coded in my entire life. Never. Sorry for the builder and not the assistant. Oh, wait, you've never coded in your entire life? Wait, what do you mean you've never? SQLiter? Of course you must have had. If you must have written a smidgen of code. Steven developed natural makeup over the years. We got some just regular face. I wash my face. Don't you do that in the morning? I mean, and then right? No, I never did. SQLiter? Well, then what? What? You need to start. You got to start, or just ask the AI to do it for you, and it will take care of it automatically. Forward self. And we're gonna go self.seq. Oh, we got an input. X. SEQ. Can we just do that? Return. I think we just do that. Right? Just like that. Keep it simple. And look how many lines of code we reduced. We made it a little bit easier. I'm pretty sure that'll do the trick. Some input art. So we're going to get a random input. Okay. Nice. I like this. This is really neat. Let me double check that this is fine before we move on. All right. Let's print. Make sure no errors. Oh, we got an error. All right. Torch.inin.model. Did we type that wrong? Is that incorrect? Torch.inin module. Okay. Module. With the, okay, so not model, module. A little bit of module there. Okay. Then we're going to create some synthetic data. Sounds good to me. All right. Training data equals torch.rnd, or is it torch.rand? Rand-in. It's going to be our batch size, comma, our input size, probably, right? Oh, dimensions, yeah, input size, yeah, okay, exactly. And then requires grad equals false, because this is detached. It's not part of the graph. This is outside of Autograd. You do use some AI. You just writes it horribly. Luckily, Neva spotted it. Okay, so, well, that kind of counts. If you use AI to write code, you're essentially kind of generating code. That is your intent. That counts. That counts a bit. Although, it makes it difficult to debug if you're not quite sure what the AI is writing. Although, you can ask the AI to debug with you. Luckily, Neva spotted it. That's great. Okay, let's keep going, you guys. Where are we at here? Oh, wow. I'm actually kind of surprised. Okay. Looking good, you guys. He's writing AI-generated C++ with lots of deoancy. What is that? What is that word? Never wait. What is deoancy? I want to translate that word. I feel like that might not be the exact word you're talking about, or maybe that was a real word. I just don't know it. What happens when the AI stops being able to understand its own code? Jinlu. Well, exactly. Then you're stuck. You're stuck. Poor guy. Major CMake issues for the first bug. Oh, really? Solace? Oh, dependencies. Got it. A lot of dependencies. CMake and building anything with those tool chains can often run into many problems, especially if you don't have the right stuff pre-installed on your system. Like you just described, dependencies. Those are necessary. Let me doom code because a girl broke your heart. Hey, sad boy. Well, good to have you here. Welcome on in. Hope you're having a good Wednesday. Doom code. We got to do some doom coding. All right. So ideal output. We're going to do the same thing here. All right. So these are labels. Oh. Features. Labels. Like that. Let's do it like that. I like that better. Features, labels. Well, you have really nice teeth. Oh, thank you, sad boy. Yeah, we had a lot of extensive orthodontics works. A lot of orthodontics. It took many years with braces. There was a bug and it made a race condition. How you get race conditions in CMake? You have no idea. I know. How would you do that? Let me go ahead and subscribe. All right, sad boy. Thank you for subscribing. Appreciate it. Good to have you here. This is the channel for software engineering. So if you're interested, we're doing some AI and we're becoming a Pytorch expert. We're following through the tutorials and we are going to make sure that we get, so we don't want, do we want batch size? We want batch size and output. So it's gonna be batch input, batch output. Hey, sad boy, thank you for subscribing. Hey, your notification comes through. You know how rare that is? You know how rare that is? That does not happen all the time. That was a special subscribe right there. That was a special subscribe. It made it through. Notifications for those don't always go through. It's like 10% chance. It's like a really low chance. Yeah, it was a good one. Thank you. Wow. I know. It's crazy. Unexpected. All right, let's close that so we can read the code a little bit more easily. And then we will open it up in the bottom so that way we can read it down there. Okay. Because our code's getting long. All right, now we've got that. Let's double check that everything looks good. Okay. So now we know why we don't want requires grad, because we don't want the Autograd engine to automatically figure out that this needs to be part of a graph of any kind. So we want to detach it. It should not be part of the graph in any way. I suppose we could also just do a detach, and that could be fine as well. The notifications depend on whether the viewer has their subscription public. Is that what that is? I didn't know that that was a feature. Jinlu, are you serious this whole time? Hey, I was going there, Volt C. I see what you said. I see what you said, Volt C. Your message is being held for review by the AI. That makes total sense. I think at least. Yeah, it sure does. Now we finally know why. Why is machine learning easy and hard at the same time? That's a really good point. Well, it's easy because some of the frameworks, like Keras, make it really simple. You can do that in just a few lines of code here. Like, look, this is it right here. Up and down, that's it. It's like a couple of pages of code, you're done. So it sounds like it's really easy. However, understanding it, that takes a little bit more of effort. It takes a bit more effort. It's pretty rough. It's pretty rough. All right, let's make our model. All right, our model equals tiny model. And then let's run it through first. Let's run first. So model, we're running forward on this features. I want to make sure this works. Print. Actually, let's do this. Out equals print out. All right, let's see if that works, you guys. Okay, Neva just solved the problem. I've been stuck on hours. Hey, you solved the SQLiter. Good job. That's awesome. Why are Junior focusing on machine learning when we already have a black box problem and 1 billion potential use cases? Oh, are you talking about the large language models? Is that 1 billion potential use cases? Hey, I try hard. Good to see you. Welcome on in. Happy Wednesday. We're still on becoming Pytorch experts. We are walking through Autograd today, which we did yesterday as well, and we're on like part 2. We're probably going to be on part 3 and part 4 of Autograd because I'm looking through the scroll and we're not even halfway down the page yet. We're not even halfway down the page. You just found the support Discord. Oh wait, really? Which one? Exactly. Looked for it on Reddit. Oh, nice. Autogradder, what is that? So Autograd is what Pytorch is essentially. It is an Autograd engine. That is their fancy word. Basically what it means is you can create a graph of connected events. See, I've got several items here. Actually, it might be easier to load up a different file. ls-1. No. How about just L? Okay, here we go. By agrad. Here we go. Let's go into agrad. When you create a layer in Torch, you can see you've got layer 1, layer 2, and layer 3. I'm going to clear some of this out so it's a little bit easier to see. We'll give you some of the Autograd detail walkthrough. Hey, Du! Hey, Du, thanks for subscribing. Welcome on in. Let's become Pytorch experts. I'm going to tell you all about Autograd right now. Are you guys ready? This is Autograd. Pytorch has a built-in sort of chaining system that allows you to apply a bunch of math to each of your layers and then allows you to run backward because it's connected each of these. It's connected all of these events. So you've got to connect, you've got your first layer here, and then you've got some sort of action or, right, some sort of activator or some sort of something you did to the tensor, right? Some sort of operation. Let's just say it's an operation. Matrix multiplication. It could be, cosine, ReLU, whatever you want. Whole bunch of different things. Autograd calculations, that makes sense. That's what we're doing. That's exactly what we're doing. Oh, okay. Autograd means you can calculate gradients automatically. Yeah, that's actually a really nice way to say it. It does. You can calculate the gradients, and it keeps track. So it keeps track of everything. So when you do dot backward, when you run the dot backward here, it will calculate the inverse of those things, right? It's like the derivative. So if you add 1, it'll subtract 1. If you multiply by 2, it will divide by 2. It's going backwards, right? So it keeps track of these things in reverse. As you perform actions forward, it will sort of log it. It keeps like a log. And it does this through a chain by every time activating this tensor right here, creating a new tensor, will keep track of what made that tensor in a chain. And so you can unwind that chain, which allows you to calculate the gradients like Neva said. And then you can apply those gradients to the original weights of the model and make it learn something. Essentially, you get to make it learn. It's optimization is what the optimization is. That's what that is. You sure know it. You know it. Let's see. Autograd calculations, that makes sense. Yep. I'm a student learning Python. Nice. Hey, Snowman. Let's learn Python together. That's what we're doing here on this channel. Indeed, let me watch so I can secretly become Dr. Gero. Wait, Gero? Wait, Dr. Gero. Wait, when did I subscribe? Oh, did you? Wait, I don't know. Did you? When did that happen? So for someone interested in this, what use case does it cover? You can build anything with AI, essentially. So you've used ChatGPT. You've used maybe some Gemini, maybe some, I don't know, Anthropic, Claude. Those are, when everyone says AI these days, they're always talking about the large language models. This is how you do that. What we're doing right now on the stream, we're learning how all the fundamentals of what makes those things work. That's what we're doing. And it's going to take a few days. Don't worry. It's going to take a few days. You can build generative AI to make text, to make pictures, and make videos. All sorts of things. The inverse of sine is arc sine. Oh, there you go. Some arc sine. Not, right? Arc sine. We get the arc sine, you guys. The inverse of sine. Is the derivative the same, though? Thank you for the hearts, you guys. Appreciate it. Should I force Neva to help you? How do you force? What's your strategy, SQLiter, to force? What is that? Anyone looking for ideas making AI vision accessible? Anything with the voice user interface or augmented reality is cutting edge. Don't make AI the product. That's my opinion. Good point. Good point, Kyle. You want to use the tech of AI to accelerate and improve an existing product or a product idea. Shutting down our computer. That will do it. Yep, that'll do it. I have this crazy AI robotics idea. Hear me out, guys. All right. What do you got? Easy to life. How's it going? What are you trying to do? We are building ourselves a knowledge base. We're learning to become Pytorch experts. That's what we're doing. We're becoming Pytorch experts. That's an evil yet effective. It sure is. That'll do the trick. Derivative sine is cosine. Yes, HS, exactly. The same as the derivative. And we like our derivatives here when we are talking about AI. That's what we're doing. In deep learning. Derivatives. We're keeping our derivatives going. All right. Sine and cosine. There you go. I need to bring AI into the place of work. Oh, all right. Need to build an AI that can build service kits based on the customer's preference. All right. So you want to use, is that Pytorch? It sure is. Yep, this is Pytorch. Exactly. We're becoming Pytorch experts. So, Rushi, is that how you say your name, Rushi? We will, in order to build a service kit based on the customer's preferences, you could probably use like Claude code in a command line fashion. So they submit a prompt, the user submits what they're looking for, and then you just have Claude code, take your existing SDK or service kits and have it customized to their purpose, create a zip file, and then provide it them to download. You could do that. That would be an easy one. I think that's probably one of the easier approaches. What is the gradient calculation with respect in backwards? Or is this a silly question? So the gradient is going to be the derivative based on the loss output, right? So you've got your output, and then you can calculate a loss. So out minus like minus 10 or whatever, which is going to calculate your loss, my loss. And then you can then from there loss dot backward, and that's going to calculate using the derivatives and the backward propagation each of the additional gradients. So it's sort of like it runs in reverse. It's going to create essentially matrices, and then you can take those matrices and you can apply them to your existing weights, your existing parameters, to help the model learn. The model basically being just a bunch of numbers, right? And so you apply it based on a learning rate. You don't want to apply 100% of the loss. You want to apply just like a fraction of the loss, like a tenth of a basis point, something like that. That's what you can do. That's exactly what you can do, a tenth of the basis point. You want to make a robotic arm that people who like art can use it to learn art fundamentals. Right. At a faster rate than normal, the device job is repetition, moving your arm accurately in the same direction. That sounds really neat. So you can have them learn how to draw more quickly. That's a good idea. That sounds like a really hard project. Because one, you need to make an AI arm robot that can draw well in the first place. There's your difficult challenge. And then you need to make it fittable on a human arm. So that way they can draw and learn how to draw that. This is the last time I'm trying interfering with her while she's working on a project. Oh, is it SQLider learning? You could running into trouble there. Hey, Cliff Flowers, good to see you. Hey, can you help me get my Replit up and running? I can't see it. You can't see my workspace. What's your Replit? What's your Replit? Is Replit? Isn't that a online? It's just an online web, right? It's an online web builder, right? Replit. Done, right? That's all you have to do. I just did it. You just go to the website. That's all you got to do. For example, draw a human in great numbers of poses, angles, and perspectives over and over again with high accuracy, building muscle memory for the user. You'll make him an artist. You will. Sad boy, you will. That's where I get confused. Do I just store the service kit data in a DB and connect to an LLM to it? So it depends, Rishi. You could. And then you could use Claude code with the P parameter, right? So you do something like, say, Claude-P, hello. I think you could do that. And then it does work for you. You can have it do work. Something like that. And it should respond. Or do nothing, right? So it performed a task. So it uses the dash P parameter. The P parameter. Hi, what's the topic? Aaron, good to see you. We are learning Autograd today in Pytorch. We're becoming experts in the Pytorch framework. That's what we're doing today. We're learning all about Pytorch Autograd. See, getting caught up on the chat messages, you guys. That's kind of cool, isn't it, Kyle? Do you use L2 loss? Regularization, right? Regularization. Loss. L2, you can do norms, you can do dropout. I've done that before, HS. Yep, I've done that before. I sure have. Today, though, we are just going through Autograd. I was not an intuitive talent artist. I really had to work hard to get out of the stick figure mode. Did you, Kyle? Are you beyond stick figures? I'm still in stick figures. Replit have become more restrictive than in the past 7 years. For example, you can only create 3 projects now. Earlier, there were no limits. Oh, Clinker Plays, really? Well, they're trying to make money now, right? Could you guys give me some tips for my project, and how long do you think it will take? It will take a while, because you're going to need to figure out how to make the art. You need to get servos. You're going to need to get the servos up and running. You're going to need, how are you going to make this? It'll take some time. It'll take some time. You can draw anything now, Kyle. Really? That's amazing. How would Pytorch relate to what I want to do? So Pytorch will help you train the model in order to learn how to draw. So that's the part of the drawing part. Oh wait, that's what Sad Boy is working on. So Pytorch, you don't want to use Pytorch for what you're doing, Rishi. You're trying to do just what you're just trying to build an agent, essentially. So you've got a bunch of data. And you can use an LLM and something called function calling tool use. Check this out. So if you want to create your own custom agent, so at Rush, look into function calling tool use. Tool use. There you go. Function calling tool use. Let me spell that correctly. Look into that for something like Anthropic, Claude, Opus, or OpenAI GPT 5.4, right? Something like that. That would be a good... Yeah, that's fair. Okay, good to hear. I'm willing to spend 1.5 years at most on this project. You will make it happen in a weird... If you spend enough time on it, you will. You'll make it work. How's it going there, Alan? Alan, good to see you. Any recommendation systems? What do you mean on the recommendation systems? That is a word that's got a lot of meanings to it over the years. A recommendation system? You're thinking like movie recommendations? What are you trying to recommend? All right, let's get back into it, you guys. So we're going to continue our Autograd adventure. Autograd training. Ooh, I like this song. Okay. So we've got our layer 2 weights, just a small slice, or the entire grad. Oh, that's why they wanted us to... Oh! So we can look at the weights directly. I don't want to look at the weights directly. I don't care that much. Optimizer prediction loss. We're going to step through this again. La 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 la. If we look at all the layers in the model, we can examine the values of the weights and verify no gradients have been computed yet because we didn't call the backward method, right? So if you were to print layer 2 and only look at just the smidgen of the data, you're going to see something that looks like this. You're going to see a gradient function, which allows you to go backward. And the layer weights. The layer weights, the parameters, the coefficients. There are all these things right here. Just a bunch of numbers. I don't know if you ever thought about that before. What are these large language models? What are they? There are all these numbers right here. They are more than that, though, of course. They're a bit more. Just a bit. Let's keep on going. All right, where are we at here? Let's see. We got our tiny model. We're going to run some input on it. All right, we'll run some input on it. All right. Let's see. Did this run yet? Let me see here. Blah, blah, blah. Autograd. We should see something here. Okay. Module is not a thing. All right. Is this here? Is this still a problem right here? I thought we fixed that. Module subclass. List is not a module subclass. Where's that a problem at? 1 second. Is that a problem? Yep, still a problem. All right. Sequential. All right. List is not a module subclass. Sequential. IAL. Did we get that wrong? Is this the part of this problematic right here? The part that I'm doing custom? I want to do this. I want to do towards sequential. Let me see if I got that wrong. Is this correct? Yeah, this right here. Quick little example. Oh, okay. We don't need to put it into an array. It's just going to do all the args. Okay. All right, you guys, here we go. It's not expensive to see if people want to pay for what you're building. Oh, it should. Oh, I'm actually kind of curious to see what you guys are going to head into there. It's kind of expensive. It could be, although it could be cheap. Rishi, oh yeah, I'm experimenting with tools and function calling. You use LangChain and LangGraph. Oh, to build something. So I guess you're on the right track, right? You sure are. Sorry. Yep. You're on the right track. You could. I tend to use directly the APIs directly instead of going into something like LangChain, LangGraph. Although you can do that, and it will help you along the way. It'll help reduce some of your code. For me, I just go straight, and I like having more access to the underlying layers. That's what I like to do. LangChain, LangGraph. You're on the right track, though. Rishi, you got it. You're on the right track. All right, now we should have no errors. Yep, no errors. Perfect. Okay. Let's get back to our output. We should see a nice... Yeah, there we go. Hey, look at that. all of our parameters on our output. So we've got a 16 by 10 matrix right here, right? 16 by 10. So if we say print out.size should be a, or is it shape? Shape? We'll do shape and size. Maybe it's the same thing. Shape and size. Size, there we go. Take a quick peek at that. All right, size is a method. All right, 16 by 10. I told you 16 by 10. And size is apparently that. Let's see what that's about. Oh, all right. Size is just a method that will invoke the shape. Okay. I don't know why it needs to be called. However that works. All right, good to know, good to know. Let's see here. All right. In the future, would you be able to go through a tutorial using the CVXPY package? Joseph, thank you for subscribing. Welcome on in. Thank you for joining. Join the right channel for software engineering. We're currently becoming Pytorch experts is what we're doing today. That's what we're doing today. Thank you for the Party Poppers reactions, you guys. What are you doing in Pytorch? We're learning it. We're just learning it. We're walking through everything. Today we're doing Autograd. We're learning about the Autograd, which is essentially just what Pytorch is. Hey there, Joseph. Hey, thank you for subscribing. Appreciate it. Welcome on in. Good to have you here. What is the CVXPy package? I'm not familiar with that package. Let's take a look. Let's see what you're talking about. What is that? Open source Python embedding model language. Oh, embedding model language for convex optimization problems. Lets you express your problem in a natural way. Let me look into this a bit more. I've not used this before. I don't know what it is. Let's zoom in, guys. Let's zoom in. You're asking about it. Let's learn. Let's learn about this. The documentation's there. What is this? Python embedded language, convex optimization, allows you to express problems in a natural way rather than restrictive. So easier. Okay, that's the whole point of usually libraries. Martin Short is wild. Wait, Martin Short. I remember Martin Short. That's actually made me laugh. Seems like they're a really good math, Mr. Steven. You have some math, you got it. All right, so CVXPY and NumPy, the problem data. All right, so we're gonna do some random. So we've got some random data, a random shape. You get an array, and you've got a number, a bias, construct the problem, objective, interesting, A minus constraints. Oh, okay. A at X minus B. All right, for the bias. So this is a machine learning right here. This is machine learning. Probabilities, the problem, result, solve, optimize. So this is optimize to return optimal value for X stored in value. The optimal language multiplier. Okay. This is machine learning. I've not used this before. It's very straightforward though. I understand it. You've got your layer and bias. Then you've got your input and you've got your output. And the result is here. And that's the labels maybe? Okay. And this is your loss, I assume. All right. That's as far as I go on that. All right, we might check that out later. Let's keep going on our Pytorch, you guys. Let's keep going on Pytorch. Where are we at here? Okay, so we want to build our optimizer, our loss, which is a very simple loss. Oh, this is mean squared error right here. This is mean squared error. Really easy. That's a really easy loss. If you've never done a loss function before, you get a mean squared error right there. Thanks, Steven. HS, you're welcome. I forgot what even you asked. Oh, you talked about CVXPy. Yeah, it looks like a standard machine learning library. Pretty straightforward. All right. I don't know why it's better or worse, because you just want to use NumPy, I would say. You could do the same thing in NumPy. So I don't know why you would use CVX specifically. Even it's importing NumPy right here. So .cp. Oh, it's got some, okay, so it's got some pre-built-in math. Okay, got it. Okay. A little bit of some pre-built-in math there. All right, you guys. Next. Okay. Where are we at here? I'm just getting back into it. Get undistracted. Undistracted, you guys. All right, so we've got our optimizer, our prediction. We're going to do stochastic gradient descent with a learning rate there. All right, we can do that. All right, so learning rate equals 0.001, I think, right? We're going to do 0.1. Okay. Then we will get our model, our optimizer equals torch dot, what was it? Optimizer dot sgd, and our parameters are the model, right? Model dot weights, was it parameters or weights? Yeah, parameters, and our LR equals learning rate, just like that. Oh, you find XGBoost and scikit-learn solves pretty much any classical machine learning. Yeah, there. Okay, got it. Now, we're learning more than we ever thought we needed to learn. This is great. I love all these connected neurons in my brain, you guys. This is helpful. Thank you, Neva. If they fall time to get deep neural networks, they fail. Yeah, they will. They're not able. You technically could maybe use a DNN pattern, although they're not built in to those, right? As far as I understand it. Hey, Catholics, welcome on in. Good to see you. What resource would you recommend for learning, studying machine learning also? So Neva, who is a Nevo there 95, recommended, well, you could scikit-learn is a good one. I jumped into scikit-learn first for traditional machine learning. Those are good. XGBoost, you could also do that as well. Or you could use NumPy and then do the math yourself. Finally, Stephen, Pytorch. Yeah, let's go. Gunheist. Yes, we're on to Pytorch. We're becoming Pytorch experts. We're going through every tutorial today. We're doing Autograd. Scikit-learn is great. I know, isn't it right? I like sklearn. I call it scikit-learn. It's actually just sklearn, right? So we do a little heart there. I love scikit-learn. Extremely principled. It sure is. That's a good one. It's a good one. All right. Let's hide these guys. So we're going to output. We got our optimizer. And we need our loss. Is going to be, I'm going to create my own loss function here. You guys ready? All right, criterion equals lambda. We're going to go x comma y, right? And then we're going to say x minus y dot pow. Dot sum. Can we do that? Is that a loss function right there? Did we just do it? Pow2. Okay, pow2. Yep, pow2. Yep. Looks good to me. Ideal output prediction. Ideal output. So this will be out and prediction. Oh no, it's the other way around. Y out. There we go. The ideal. How about we do this? Ideal. We'll just do it like that. So that way we can see what our criterion is right there. Right there, we got our criterion right there. It's going to text you the math in a... Pytorch just won't. Like, reading the scikit docs is amazing. Yeah, that's a good point. Scikit-learn, fantastic. If you're trying to do standard machine learning, regression, classification, I like to support vector machines, SVR, SVM, SVC, right? Those are great. I like those. Those are really fun. That's my favorite. Especially in data science. In the business realm, those are really powerful tools. Those are really powerful tools. Because what you can do is you can give it a whole bunch of data, a bunch of different data input parameters, like the current year, the day of the week, maybe, you know, what group this is, what cohort this is, and have a whole bunch of input data. And then you can predict based on other data that you've seen in the season to see what your potential revenue is going to be. You can do fun things like that. It's really neat. Also, many actual machine learning problems can be solved by Pytorch and can be solved by scikit-learn because of data. Oh, they can't be or can be? Oh, they can't be solved. Got it. You need the data. You do. It's all about the data, you guys. It's all about the data. All right, let's keep going. So we got our criterion. We got our output. We got our optimizer. Now we say out dot back. No, not yet. We need to do our loss equals criterion. Then we're going to say the output. See, our out, comma, labels. Write that, right? Out, comma, labels. Ideal. Yes, perfect. Okay, like that. A little confusing. It's not a problem though. And we say loss dot backward, like that, and then we can optimize. Much love, bro. Hey, Santanix, good to see you, Santanix Ferguson. Hey, in which door a guy with my skills could start knocking, falling 33 times? Oh, failing. Is it failing 33 times on a deploy is funnier than editing video these days. Wait. Failing 33 times on a deploy is funnier than editing a video. 33 times is a lot of times to fail on a deploy. It really is. Like 1 or 2, okay, sure. 3 or 4, now we're getting to crazy. 33, you're in a whole new world of your own. That's a new record. Traditional machine learning needs like a few orders of magnitude less data to compute. Ah, yes, good point. That's a good point, Neva. Yes, traditional machine learning, you don't need that much data. You don't. You just need enough to find a trend. Just enough to find the trend. Because your regression is only a dimension or so. It's only like 1 or 2 dimensions. That's a lot. He's using Windows. Yeah, I know, right? He's using Windows. Are you using Windows over there, Santanix? That's a lot to fail to deploy on. So now we can calculate our gradients. Then we are doing something. Then we need to do optimizer.step. Oh, wait. Optimizer.zero grad. Zero the gradients, I believe. Right, you want to always do that first. Zero the gradients, and then optimizer.step will apply, based on the learning rate of our optimizer, the gradients that are calculated in our back propagation. Oh, thank God my algorithm is not messed up. All right, good to hear. Hey, Zero, wait, how do you say your name though? Zeus? Bunch of loud kids and Chinese cooking in the games. Is that part of the distraction that's making it difficult for you to achieve your objective? You got some distractions, do ya? You got some distractions over there? All right, do we do this properly? Or do we got some errors? We got some errors. Torch optimize. Oh, I gotta spell it properly, right? Optimizer. Wait, is that not how you spell optimizer? No, I know how to spell things. Optimizer. Right there. Torch optimizer. Oh. It's not optim. It's only optim. What? Why are they short? It's just a few letters different. It's just 4 more letters. Come on, guys. It's just 4 more letters. They could have at least had some weird alias in there. It's fine, though. It's fine. You're a fresh one. Much better. Loving this. Hey, good to hear it. Good to have you here. This is a lot of fun. I'm enjoying this. We're learning how to build with Pytorch in the best of ways. And we're going to become Pytorch experts. We're learning all the things. All right, so we created our own criterion, and we got our loss. Then we're going to do backward. And this is going to give us our output. Yeah, sure is. I wonder if you can do a dot sequence. Print model dot sequence. What is that going to give us? Is it going to give access? I think it's going to give us access to all the layers. I'm pretty sure it is. Hey, how's it going there? Inop Facecam. Inop Facecam, it's been a while. Welcome back. Good to have you here. Has ever happened? So, hey, Santanix, Ferguson, that after a failed deploy, you have a total different app. Oh yeah, sometimes. By the way, just got 3 months on the Vibe thing and recently jumped into Linux. I hook it up with a VM running its Tailscales global VPN. Santanix, now you're getting into it. You're in deep now. You can't stop. You got to keep going. You're doing it right. Santanix, that sounds great. I just sent a video of your new favorite sporting algorithm in general. Jinlu, we'll check it out here in a bit. I want to fix this problem that we got here real quick before we check it out. Hateful word, full of word namings. Oh, on Java. Oh, Java. Yeah. Oh, Java. You think about Java. And on Facecam, good to see you. By the way, I don't know if you remember me. I'm Nick Cannon editor. Oh, a little bit. Yes, you've changed your name. Okay, so you changed your name. Nick Cannon. Yes, I do. I do remember that. I do. Stephen Math Skills, spelling and grammar B+. I know, Kyle, you know. I'm just typing really fast. Also, I spelled it properly. It's just that they named it differently. They changed the name. They truncated it. Cyber Potato, good to see you. Welcome in. And what are we doing with our lives? We are becoming Pytorch experts. Focus on your programming language. Hey, no worries, Facecam. Good to have you here. Linux is really neat. It sure is. I love it. Hi, buddy. How was it going? I guess it was too late. Hey, Gokul, you're good to go. You're good to go. We've got some time. Oh, wait, let me check my calendar real quick. Let's see here. All right, check my calendar. Okay. We've got some time left here. We got a little bit of time left. All right, I'd like to get through this segment of Autograd is what I'd like to do. Hi, buddy. Don't worry about being late. You're good. You're good. You're at a very interesting part, I think, of this. So we just learned Autograd. Autograd is the entire Pytorch framework, essentially. It creates a connected graph for every operation that's performed on a tensor, and it's stored. It's stored inside each of the layers, or whatever, every tensor, and it connects back up to the previous layer that was being interacted with. So if you have a fully connected graph, that means that you can run full backward propagation, creating new gradients, which are additional matrices. They're just matrices that are based on the inverse. And if you do that without applying a loss, you essentially have the ability to create a full flat graph, which is not useful. What you want, though, in AI world, when you're training, you need to get the actual ideal. You need to create a loss. You need to subtract what the output of the model gives you with the ideal target data. And then you take that back through Autograd, recalculating derivatives and the inverse. That will create additional matrices that you apply to the weights of the parameters, which we have right here. We've got two layers. This is layer 1, and we've got layer 2. Well, layer 2 and 1 right there. So that's what we're doing today. We're learning about Autograd, and we learned a lot. Just a little bit of time. Just a smidge. You got it. My manager is promoting AI usage, and I don't consume at least 300 tokens a month. He'll get angry? Well, you can consume 300 tokens instantly. That is like a real quick one. 300 tokens a month isn't that much, right? It's not. Yeah, it's not. It's a very small amount. It's essentially 300 words, about, right? 300 words or so. You could do that in an instant, in about a minute. You eat 300 tokens for breakfast. There you go. Maybe 300,000. Okay, got it. 300K, sure, there you go. So here's the deal. It doesn't make sense to sort of incentivize using more tokens. I think it just makes more sense to, use the AI and learn how it makes you feel happier, because now you don't have to type so much anymore. It's like a nice, giant, enormous paintbrush that types everything for you. Automatic keystrokes engine. I love it. All right. Let me get through this one thing, Jinlu, real quick. We're going to step on the optimizer, and then we're going to get our outputs here. One moment. Let's make sure this works. Hey, there it is. All right, check that out. So, all I have to do is print this out real quick. So, what if we do 0? So, let's layer 1. Let's do, well, they want layer 2. So, let's go to 0, 1, 2. All right, let's try that. Let's try that real quick. All right, making our way. Why not go from data entry to advanced review strategist? It's a no-brainer. It's a no-brainer. 300 premium tokens, whatever that means, a bunch of corporate... Yeah, it is. It sure is. You know it. There's no reason to incentivize consumption of tokens. My programming language got 20 plus stars this week. Hey, did it really? Because I created a marketing technique by Claude to contribute to the list. Basecamp. All right. I think Kyle and I would really like to know what you mean by that. You got to tell us more, Facecam. Tell us more. Tell us more. I think Kyle and I would be interested. Yes, Kyle and I are very interested. We're very interested. Super interesting. super interested. All right. So where did we do this? All right. 1 second. Okay, so I want to see the gradient. Let's do the weight.grad. Okay. Sequence2.weight. Is it weights? I feel like weight is not the correct term. I feel like it needs to be plural. Here's the gradient. Right there. That's the gradient. And it's going to be 16 gradients. Wow. 16, yep. 16 gradients. That is really neat to see. It's neat to see the internals of Pytorch is accessible right there. All right, that's what I wanted to take a look at. All right, Jinlu, what do you got over here in general? Vibe sort. I'm concerned about this one. I'm concerned about this one. Okay. All right, you guys. All right. All right, wait. Let's pull that up. I'll pull that up. I don't know if you guys got that. I don't know if you got that. Let me pull this up here. Vibe sorting, an AI algorithm. Oh, it didn't finish. 1 second. All right, one moment. Let's just keep watching it. An AI-powered sorting algorithm. It sends an array to a large language model, and it prays it doesn't hallucinate the output. Look what it did. It tried. It got part of the way there. Look, it got part of the way there. It didn't finish, but it got part of the way there. Oh, that is hilarious. That is hilarious. That is great. All right. You shared on Facebook. I really like that. That's hilarious. You shared on Facebook, got many haters. Interested people, they hate the project because I am using AI even though it's just marketing technique. Oh, got it. Okay, understood. All right, I gotta update that. That was funny. Thank you for sharing that. That was worth it. That was absolutely worth it. There's also Miracle Sort, which waits for the cosmic ray to bit flip until please bit flip. It's a real thing. It's a real thing. So you need to wait for a very, very, very powerful cosmic atom that has been hyper accelerated by probably an exploding star or something, or a some sort of cosmic event, super accelerated to the speed of light, near the speed of light, shoots down through the atmosphere and hits one of the transistors or something like that on your computer, right? To flip you, in this case, it would be a memory chip. That is going to take forever. It'll take forever to do that. Miracle Sort. Didn't know you should develop more. You should. One of those rays hit a digital voting system and gave someone 4,000 extra votes. I heard about that. That was real. They're like, how did this even work? Oh, the vote counting system failed. And it wasn't that the vote counting system failed. It was attacked by particles. It was by one very heavy particle coming from space, you guys. All right. That was awesome. That was fantastic. All right, we got a few minutes left here. 20. We do 20 minutes here. We'll do 20 minutes. All right. Great to have you guys here. All right, let's make our way. Let's keep going with our Pytorch Autograd. Let's make this happen. So we saw our model. I updated it a little bit. I changed it a bit from the tutorial because I wanted to do it my own way. I put it inside a sequential. I like doing this better because it makes the forward pass really easy. Look at that. Look how easy the forward pass is. Stephen Hawking. Oh yeah, Stephen Hawking. Well-known famous scientist. Very well-known famous scientist. Was Hawking radiation. I remember that. The final is their ChatGPT sorting algorithm. That's exactly what that was. That's exactly what this was right here. This is what Jinlu posted. That's exactly what that was. Oh, you've got a Thanos sort. All right, we got to check this out now. We got to go through the Thanos sort. 1 second. Just delete it until it's in the right order. Hey, there you go. Delete everything. Delete 50% until it matches the Thanos sort. And it works, although you lose a lot of data. I love this. Okay, that's pretty funny. I like that. Perfect balanced, as a thing should be. Perfectly balanced. There you go. I like that. Okay. Genuinely, that's so cool. It is, yeah. This YouTuber has a lot of videos on random sorting algorithms. It's fun to watch. Nice. That's awesome. All right, so now we've got our gradients. So let's go to the next phase, you guys. Let's see where are we at now. Let's close this, bring it back over here. Okay. Step 0 grad backward and the loss. So this allows us to train on the model by doing this in a bunch of steps. Wait though, there's a problem. There's something missing here. This range, we'll run it through 15 batches. Prediction loss backward, prediction loss backward. Does this, what does this do right here? 0 grad, set to none, false. What is this doing here? Hold on, let's read through this because this is weird. This is weird. There's something weird going on here. All right, one important thing about the process, after calling step, you need to call grad. We know that, or else every time you run backward, the gradients on the learning weights will accumulate. Really? Okay, we knew that, but I thought they got overwritten. They don't get overwritten, they accumulate? So let's look into that. Let's look into that real quick. I don't know what that means. What does accumulate mean? Does it mean that the same gradient is being mutated? Or does it mean that it's creating an array of gradients? Is that what that means? So there's more gradients? There's more than one gradient. It will do more than one gradient. Hold on, hold the phone. Hold the phone. So backward, backward, backward. We could just keep running backward. We don't need to do this. Let's run backward a bunch of times. All right, let's try it. Let's try it. I'm very curious about this. So we'll do this. Backward, backward. A whole bunch of backwards. And then we should see, if we print this out, we should see a whole bunch more data. Oh, that was a problem. It didn't like that. Why didn't it like that? Let's try this again. Hold on. Oh, it might not let me. I need to recreate it. One backward per. Okay. Let's see if we can make that work. All right. We can do this again, guys. We can do this again. Lost criterion. Can we do that? Is that going to allow me to do that? One backward per. Nope. Okay, so we need to do another out as well. Let's try this. Where's that out here? Oh, right here. Okay. Boom. All right. Can we do it a second time? Yes. Okay. So instead of giving you a nice error warning, it's just gonna crash straight out. If you ever run into a scenario where you reuse and you try to rerun a backward, it will fail, and it fails right here. Here. Oh, actually, okay. So it does give you a nice error. I was wrong. It gives you a nice error. Check this out. Here we go. Let's read through this real quick. Let's read through this. Okay. Trying to backward through the graph a second time. Right there, that's what we were trying to do. And it won't let you. Or directly accessing a tensor after they've already been freed. Saved intermediate values of the graph are freed when you call backward or autograd.grad. Specifically retain graph true. Oh, specify retain graph true if you need to backward through the graph a second time, or if you need to access saved tensors after calling backward. Let's try it out. Reading the error messages, you guys, check that out. Retain graph equals true. Let's try it again a second time. Is it going to error out now? No, it gave me something different. So we tried retain graph. Got unexpected key. Wait, that's what it told us to do. It told us to do that. Hold on. Let's get the error again. Use retain graph true. Right there, right? Where else would you put it? Oh, retain, not retain. Oh, I spelled it wrong. It's the Steven spelling problem, isn't it? It's the Steven B+ grade spelling. Got it. You should rewrite all the PyTorch tutorials. I know, right? We should rewrite. We could make our own. We can make our own dedicated PyTorch tutorial. All right, thank you, Neva. Appreciate it. Oh, wait. Okay. We did it. We. One second. We'll try this again. 1 second. All right. Trying to backward. Use. I specified retain graph. All right, so that time it didn't error, but it gave me the same error, even though I specified it. Look right there. It's telling me. Do it on the first backward. Oh, okay. Let's try that. Thank you, Jinlu. Let's try that. First backward. And then we could do it on the second backward as well. You might as well be able to do it on both. Oh man, okay, hold on. One of the variables needed for the gradient computation has been modified by an in-place operator, which is the output of 0 at version 2, expected version 1 instead. Enable anomaly detection to find the operation that failed to compute its gradient with Torch Autograd. All right, let's enable anomaly detection. We're gonna go down the rabbit hole here. We don't know where we're gonna go here. We're outside of the tutorial, you guys. We're in weird zone now. All right, let's try that. What is the deal? Does it help? Did it help? No, I didn't do anything. Okay. Detect. Oh, wait, no, it's right here. Right here, you guys, right here. Okay. Error detected at atom backward 0. No forward pass information available. Enabling detect anomaly. Oh, we just did that already. Okay. Okay. La 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 la. Okay. Hello, Mr. Positive Adam. Mister, welcome on in. Good to see you. Happy Wednesday. We are getting our abilities upward and onward with Pytorch. Turning Autograd on and off, right? How would you do that? Okay, so you requires grad true or false. You could also set eval on, right? Eval mode. You can do eval mode. We're just recalling things, right? We're recalling things. Inference mode. Inference mode is what you want. Right? And there's a couple ways to do it, right? So this is definitely one to turn that off. Torch.nograd. There we go. Torch.nograd. Just like that. Formulation. Wait. Form you Montana, Alabama. Wait. Thank you for subscribing. I appreciate it. I didn't see your name long enough to read it on the screen. Thank you for subscribing. We're becoming PyTorch experts. Let's do this together. We're learning everything we possibly can about PyTorch. Today we're doing Autograd. We're only 50% through the Autograd tutorial, which I'm really surprised about. We're going to have a part 3 here, aren't we? You put your dinner on general real quick, Jinlu? I'm actually kind of curious. I am hungry. It is extra food time. It sure is. Oh, nice. Look at that. All right, potato. You've got a arugula or rocket. I don't know what you call it over there. Arugula or rocket. And you've got some lettuce, iceberg lettuce. And if I zoom in here, it looks like kidney beans and corn. There you go. That's actually something I would eat. You're eating what I would eat. That's what I would eat for dinner. Very nice dinner, Jinlu. Yep, vegetarian chili corn carne. Ah, yeah, nice. That looks very good. Chili con carne with mashed potatoes and salad. There you go. You're good on the vegetables. You're good. Not everyone does the vegetables. Usually in American diets, it's just some sort of animal product and then a refined product like pasta. And that's it. That's usually what they eat. You ate Cinnamon Toast Crunch? You did? Did you eat Cinnamon Toast Crunch? Oh, I love that. That's like one of the best cereals. It's such a good one. All right. So let's go through. All right. So we got 10 minutes here, you guys. Turning on and off Autograd. So there is a requires grad, and there's also a torch.nograd, which you can use as a wrapper, right? What is that called? What is the @ wrapper? What is this called again? It's a wrapper function that allows you to specify. It's an annotation of some sort. Yeah, in American, either is bioengineered chicken or in a can. Yeah, exactly. It would be. It sure would be. I'm just going to read through this really quick so I see where we're at here. Oh, Torch.enable grad will enable it. You can also detach, which will disable it as well. So there's a lot of ways to escape the auto gradient. There's a lot of ways to escape the gradient. No grad, inference mode, and you've got the grad false and detach. That's 4 methods right there to escape the gradient, the auto gradient. That's pretty neat. There are situations where you'll need finer control over whether gradient is enabled or not. There are multiple ways to do this depending on the situation. The simplest is to change the requires gradient flag on the tensor directly. And we did this earlier, guys. We sure did. Hey, Cool Hand Mac. Holy plastic surgery, Batman. I see what you're talking about there. I know what you're talking about. Now, I'm just old. This is what old people look like, you guys. Old people. I'm in my 40s. Hey, give me an idea problem to vibe code. Santanix Ferguson, how far do you want to go? My favorite is if you bring something into the real world. Let's bring something in the real world. It's impressive. So something in the physical world that is being controlled by a large language model with function calling and tool use. Build an agent that controls something in the real world. There you go. How's it going there, Sraimi? What are we doing today? We are becoming Pytorch experts. We're learning Autograd today. We're 50% the way through the tutorial. That's what we're doing today. Hi, Steven. Have some questions. Are you aware of what is that? Meta Scalar Hackathon. Oh, Meta AI Scalar Hackathon. I'm not. I don't know about this, Vasu. I've not heard about it. Tell me about it. For Gen Z, the old term applies to anyone older than 18. The old term. Yes. Oh, got it. Okay, Jinlu. Understood. Yes. I'm very old then. Let's put it that way. I'm extra old. Ageism is a psyop. Extra old. So anyone older, yeah, exactly. So those of you who are in that range, I'm extra old. Eric and Vivian, thank you for subscribing. Welcome on in. We are becoming Pytorch experts, you guys. Let's continue onward. We'll get through these turning the Autograd on and off. We'll do this tutorial real quick. Oh, Jinlu, your dinner just popped up there again. All right, that sounds really good. All right, so we're going to close that. We're done with that part of Autograd, and now we're going to go into turn off Autograd.py. Python turn off. Okay, import torch. A equals torch.rand. And then we'll go 2,2. Hey, Garrett Workman, thank you for subscribing. Appreciate it. Welcome on in. You joined the right channel for software engineering. We're going to be learning some really interesting things in PyTorch throughout the next week here. I'm 41 years young. Me too, Taskash. Me too, Taskash. We're similar ages. We are similar ages. We are in our 40s. You've used OpenCV, which kind of confusing, and it's had to create a real RL model, and you're not sure exactly what to do. So you're kind of looking for any answers from you. The OpenCV is what I think you're right. Open Computer Vision. I'm pretty sure that's what you meant. That is, it's pretty straightforward. You can do that. That works. Actually, you need to provide me with details though. What specifically are you trying to achieve? We can walk through that. What specifically are you trying to achieve? Oop, Jinlu, your dinner's back again. It just keeps popping up. Okay. All right, here is 1, 2 required grad. Okay, so we're gonna, and then we'll say requires grad false to turn off Autograd. So Autograd will not be calculated on this tensor. We don't have to worry about that anymore. Your dinner just has that awesome, it kept popping up, it kept coming back. All right, so this wants to be true. All right. And then we can do a.grad false. You can do it right there. And this should give us an error, right? No, it won't give us an error. It just won't compute the gradient any further, right? Is that how that works? All right, let's find out, you guys. Let's find out. B equals A times 2. And we could say B1. Oh, all right, we'll do B1 and then B2 equals A times 2. We could do that, right? Same thing. A times 2. Print B1, which should say that there is a gradient. However, if we turn off the gradient, right, you can turn it off right here. I didn't know that you could turn it off right here. This is neat. Okay, so we are learning something new. You can turn off the gradient, Autograd, detach it, or allow this leaf to no longer be part of the graph. Bro's typing code. Bro must be AI. I know, right, man? Good to have you here. Welcome on in. Fun stream. Have been a beautiful day. Sergio, thank you. Serge, thank you for doing it. Thank you for being on in here. Can I provide a link in the hackathon directly? So yes, you have to do it on the Discord, Vashu. Do it on the Discord. So click this button here. If you're not already at Vasu. There's the Discord link for you. Right there. Good to have you guys here. Just came back after a few hours to say bye. Because I didn't say. All right, SQ Liar, thank you for saying goodbye. We'll see you tomorrow if you stop on in. We're going to be continuing our Pytorch adventures. You guys. A dot, was that require grads? Requires grad, again, it's the same thing, okay. Requires grad equals false. And then we print B2. So we're going to see one that has an attached gradient, and this one will not. So that's what we should learn from this little segment. There we go. Or a complete giant error. Did I type it wrong? Torch.rand. Did I type this wrong? Yeah, I usually do. Rand ones? We could do that. That'll be fine. We'll just change it to ones. Okay. Ones received an invalid combination of arguments. That's a perfectly fine combination of arguments. What are you talking about? That is a perfectly fine combination of arguments. Thank you. That is. Sure is. What is it talking about? Tuple ints. Well, do I? No, that's perfectly fine to me. Requires grad. Did I get that right? R-E-Q-U-I-R. Grad. Okay. That's why. It's Steven's spelling issues again. Okay. Now we're good, right? Now we're good? Yeah, now we're good. Okay, good. Good. You got an Easter holiday next week. The week after that, might participate in a game jam or something. Jinlu, that sounds like a good plan. The spelling of requires grad is wrong, mate. It sure was, Marin. You know it. All right. I'm like, why is that not working? It looks perfectly fine. Spelling. I'll be finally completing your fine-tuning an LLM model this week. Hey, that's great. This is my first time. Well, congratulations. That was a lot of fun, right? You made it better, or you made it your own. Hey, Mohammed, do you know a website that can find projects like Enigma machine projects, simulation of it, or something like that? I do not. I don't know what that would be. I don't know. You would have to just search around until you found it. That's all I know. Should I do a Discord video call? Yes, Kyle. Oh, yes. Oh, thank you, Kyle. All right. So we're wrapping up, you guys. Had a lot of fun today. We will continue tomorrow our Autograd adventure. And we are halfway through, so we're probably going to do a part 3 and maybe even a part 4 of Autograd. We're going to learn all about Autograd. Thank you, guys. Much love. Appreciate it. We'll be back tomorrow. Have fun, guys. We'll be back tomorrow. Enjoy the rest of your day. More PyTorch tomorrow. We're going to become PyTorch experts. That's the plan. All right, have a good one. Sounds good. All right, bye, guys. See you tomorrow. Bye, everybody.